Hello, my name is Angus Hughes, and in this video presentation I'll be giving you an insight into the physics and applications of stress and strain. Firstly, I'll begin with stress. Stress is defined as force per unit area. It has the same unit as pressure, and in fact pressure is one special variety of stress. However, stress is a much more complex quantity than pressure because it varies both with direction and with the surface it acts on. There are a number of different types of stress, such as compression, tension, normal, shear, hydrostatic, and directed. Compressional stress is stress that acts to shorten an object, whereas tensional stress is stress that acts to lengthen an object. Normal stress is stress that acts perpendicular to a surface. It can be either compressional or tensional. Shear stress is stress that acts parallel to a surface. It can cause one object to slide over another. It also tends to deform originally rectangular objects into parallelograms. The most general definition is that shear acts to change the angles in an object. Hydrostatic stress, usually compressional, is stress that is uniform in all directions. A scuba diver, for instance, experiences hydrostatic stress when diving underwater. Stress in the earth is nearly hydrostatic. The term for uniform stress in the earth is lithostatic. Directed stress is stress that varies with direction. Stress under a stone slab is directed. There is a force in one direction, but no counteracting force is perpendicular to it. This is why a person under a thick slab gets squashed, but a scuba diver under the same pressure doesn't. The scuba diver feels the same force in all directions. Now on to strain. Strain is defined as the amount of deformation an object experiences compared to its original size and shape. For example, if a block 10 centimeters on a side is deformed so that it becomes 9 centimeters long, the strain is 10 take 9 divided by 10, or 0.1, sometimes expressed in percentage, in this case 10%. Note that strain is dimensionless. There are also a number of different forms of strain. Longitudinal or linear strain is strain that changes the length of a line without changing its direction. It can be either compressional or tensional. Compressional strain is longitudinal strain that shortens an object, whereas tensional strain is longitudinal strain that lengthens an object. Shear strain is strain that changes the angle of an object. Shear causes lines to rotate. Infinitesimal strain is strain that is tiny, a few percent or less, allows a number of useful mathematical simplifications and approximations. Finite strain, however, is strain larger than a few percent, requires a more complicated mathematical treatment than infinitesimal strain. Homogeneous strain is uniform strain. Straight lines in the original object remain straight. Parallel lines remain parallel. Circles deform to ellipses. Note that this definition rules out folding, since an original straight layer has to be straight. Inhomogeneous strain is how real geology behaves. Deformation varies from place to place. Lines may bend and do not necessarily remain parallel. The stress and strain graph is an important tool in materials analysis. It is a means of determining the behavior of a specific material and is generated by conducting a tensile test on a material. It allows us to divide materials into two broad categories: ductile materials and brittle materials. Ductile materials are materials that undergo large, permanent strains before failure, such as steel and aluminium. Brittle materials are materials that fail with little elongation after yield stress, such as ceramics and concrete. This here is a stress-strain graph for low-carbon steel. As you can see, the first part of the graph is linear. This represents the elastic deformation, where the material will deform but return to its original shape. The slope of this section of the graph is equal to the material's modulus of elasticity, or Young's modulus. The next section of the graph is the yielding region. This region begins at the apex of the elastic deformation region, otherwise known as the yield stress. This is the point where permanent elongation begins to occur. As you can see, the slope rapidly decreases until it plateaus and remains near horizontal. In other words, a large strain increase, but a low stress increase. The next region is the strain hardening region. After undergoing large deformations, the metal has changed its crystalline structure. The material has increased resistance to applied stress. The end of the strain hardening region is the maximum stress, which is the ultimate stress value. This is the beginning of the necking region where the stress decreases until eventually rupture occurs. I'll now go through some basic stress and strain calculations. This here is normal stress, which is equal to force per unit area. Normal stress acts perpendicular to the cross-section and results in a change in volume of the material. This calculation assumes that the stress is uniform over the cross-section. If the stress varies, we write the calculation like this. We generally assume that the force F is evenly distributed over the cross-section. In reality, however, F is equal to the resultant force over the end of the material. Unlike normal stress, shear stress acts tangential to the surface of the material, which results in a change of shape. With shear stress, we do not assume that stress is uniform over the cross-section because this is not the case. Therefore, shear stress is defined as this equation, which is an average stress. Normal strain is defined as the deformation per unit length of a member under axial loading. Normal stress is dimensionless, but can be expressed in several ways. This diagram here shows a material with an original length of 100 millimeters, which is deformed by 0.01 millimeters. Therefore, the normal stress is equal to 100 divided by 0.01. Stress and strain have many different applications in the real world, mostly in the engineering and material science fields. In geotechnical engineering, for instance, stress and strain are used to determine the amount of force a particular soil can withstand before failure occurs. Or structural engineering, where stress and strain are used to determine the deformation of a structural member and the amount of force that will be applied before fracture occurs. These are only two of many different applications for many different fields of study. I encourage you to research more about stress and strain based on your own field of study. So now you have a basic understanding of the concepts of stress and strain. I hope that this presentation will help you in your future projects. Thank you for watching.